Good morning, everybody. Or good day, or good 11 a.m., whatever. So, you might notice that today is a bit of a special day because we have not one guest at the IvS, but two at the same time. So these are Jan van Roestel and Steven Bloemen, both from the University of Radboud in the Netherlands. And Jan has done his PhD, I believe, was it in Amsterdam or Radboud? No. Now in Amsterdam. Okay, I've got this switched up. Wonderful. With Professor Paul Groot, if I remember correctly. And then Steven did his PhD somewhere else with some Professor Connie Eerts or whatever, I don't quite remember. And as in the last few years, they've been playing a very pivotal role in the BlackGEM project, which is what they will be telling us a lot more about as of right now. So please take the floor.
Yes, thank you. Does this microphone work? Yeah, good. Well, very nice to be here again. As Matthijs said, I studied here in Leuven. I did my bachelor's, master's, and PhD here. So very nice to be back and talk to you about the BlackGEM project, of which you're all part, whether you know it or not, because Leuven is one of the big partners in the BlackGEM project. So BlackGEM are these three telescopes here in front, the three funny-looking towers that are at La Silla in Chile. And the main purpose for which we built BlackGEM was to study the electromagnetic counterparts of gravitational wave sources. Now, gravitational wave sources is a field that really started in 2015 with the first detection of a binary black hole merger. And since then, this field has moved to now more than one detection per week. So what was a niche thing less than 10 years ago is routine right now. So there are various detectors, LIGO in the US, Virgo in Italy, Kagra in Japan. And they have several observing campaigns. So currently they're in campaign 04, which was interrupted for a few months to do technical upgrades, but it's starting again right now, this week. And as you can see here on top, the distance at which they can find sources, in this case double neutron stars, merging is increasing campaign after campaign, and that is why the number of detections with time increases very rapidly. So there's a variety of sources already found. Most of these are black hole mergers. Every line here essentially indicates the mass of the two stars that have merged into the more heavy one on top. And all these blue points are black hole mergers. Here on the bottom, there are a few that involve neutron stars. It's harder to find those because of statistics, the number there are. Also because the gravitational waves that these systems produce are not, don't have the same strength as the black hole ones because of the lower masses. So these are lower in number, but for BlackGEM's point of view, those are the most important ones. So we are after the neutron star mergers. The reason for that is simple. If two black holes collide, then you don't expect any light to come out of the system. But if you have a double neutron star, then this is what happens. So the two stars collide, and then you have nuclear reactions and ejecta into the universe. And in this process, especially the nuclear processes here, light is produced. And that light we can observe. And that is the goal of BlackGEM. Now, one of the reasons why these neutron star mergers are important is the chemical evolution of the universe. So this is a periodic table that is colored depending on the origin of these elements. And here you can see that essentially the majority of the bottom half is predominantly produced in merging neutron stars, because you need a lot of neutrons to be captured to make these nuclei. So neutron star mergers are the place in the universe where we expect this to happen. But it is, to a large extent, theory, modeling, and we want to see this in action. Now, these double neutron stars, when they are seen with gravitational waves, then the gravitational wave detectors can localize them on the sky, but that localization is very poor. And that is the main difficulty when you also want to find the light that comes from these systems. So typically, for the detections that LIGO and Virgo make, you'll end up with a sky region of 100 to 200 square degrees. So the moon is half by half a degree. So you have to scan a very large part of the sky to find the light from this explosion. The sources are faint at the typical distances where these are observed by LIGO and Virgo. You expect something at 22nd magnitude. And they're very short-lived because it's these nuclear processes and these decay at a time scale of days. So you have to be fast, you have to find a faint source on a large part of the sky. And that is the difficulty we face, and that is what BlackGEM is built for. So far, this has been done once. So there was one double neutron star merger that was seen in gravitational waves, but also in electromagnetic signals. Here you see the gravitational wave signal, and 1.8 seconds later, there was a gamma ray burst observed by several instruments. This was in 2017. Now, this was quite a well-localized and bright event. So in a sense, this was a lucky shot. The majority of them will not be this bright. And the optical counterpart was also found by a telescope in Chile, SWOPE. And you see that the localizations where the gravitational wave event was seen, where the gamma ray bursts were seen, and where the optical counterpart was found, they all overlap. So this was the same source. So far, this is the only example where this has worked. And you can see here what it looks like. So this is an old image taken 20 days before the gravitational wave was seen of a galaxy. And here you see the same galaxy, but 11 hours after the gravitational wave was seen, and there's an extra source here. And that source is the light that comes from this neutron star merger. So that's what we will try to do. So you have a detection by LIGO and Virgo. You get a rough sky position. We will tile that and scan that whole region with our telescopes, find the source with the BlackGEM telescopes, and then follow it up with larger facilities to take spectra and everything you want to see in the few days that this event is visible. So BlackGEM was 10 years in the making, just to give you an idea of how these projects go. I finished my PhD here in 2013, May 2013. That was just after the first proposal was sent in to the Dutch Research School for Astronomy. Then I moved to Nijmegen in the summer of 2013. We started working on the preliminary design. The year after, KU Leuven joined the project to build the cryostats of these telescopes. A year later, we had our final design ready. Then we started building a prototype, which is now installed in South Africa. And then we built the BlackGEM telescopes. Then came COVID, which knocked us out for a few years because travel to Chile became very difficult. So ultimately then last year, 10 years later, we started the operations of these telescopes. So here's a model. You'll see pictures later of the telescopes. So there are two projects, Meerlicht and BlackGEM. They're very much linked. Meerlicht is installed in Sutherland and is the prototype. Has a different consortium, also largely a different science goal. And BlackGEM are three of these same unit telescopes at La Silla in Chile. And Paul Groot is the PI of this project. And as you can see, there are many partners now in the project. The main ones are the Dutch Research School for Astronomy, Radboud and Leuven. And then there are various partners that have joined essentially to do other science with the same data. For example, variable stars, asteroids, and so on. So Jan will talk about that part later. They're specifically designed for gravitational wave follow-up, but you can do lots of other things, of course. And we built the whole telescope around the CCD. There are not many large CCDs that you can buy off the shelf, so if you don't want to design something yourself, then you're limited in your options. So we first chose the CCD, that's a 110 megapixel CCD, and then we built a whole optical design of the telescope to get the image we wanted on that detector. And then we built a mechanical design and everything that comes with it. So in the end, we went for a 65 centimeter primary, which gives us a 2.7 square degree field of view on this detector. And that is the best balance that we could find between sampling on the sky and depth and field of view and price, of course. Here are a few pictures to give you an idea what the telescope looks like. So this is the moment that the primary mirror was being integrated on its mirror cell. As you can see, a 65 centimeter telescope can be handled by a few people. The next picture shows the lens tube. So there are 3 corrector lenses here to give a nice flat focal plane on this 10 by 10 centimeter detector. And in the back here, you have the carbon fiber structure, and that is the telescope itself. So this carbon fiber structure is made such that the telescope is completely athermal. So the carbon fiber can be made such that it expands when the temperature drops. And the metal elements do the opposite. So altogether, the distance between the secondary mirror and the primary mirror is kept constant, and we refocus the telescope 2 times a year. So that helps certainly in robotic operations to make it reliable. Then we did a first test on the parking lot in the Netherlands. Of course, you're a bit limited in what you can do, what you can see, but at least we could verify that all the optical elements were well integrated and that the image quality was reasonable. And then we have 6 filters. That's one of the features that sets us apart from some other wide field telescopes. Since we have this one CCD and 10 by 10 centimeter focal plane, we have a filter reel with 6 filters, and we can rapidly change between those. That is something like that telescopes like Vera-Rubin, for example, or ZTF cannot do so easily. So we have 6 filters. It's a Sloan set, and then there is an extra wide band, sort of a V+R band, which is our most sensitive one. Then in 2018, we installed the prototype at Sutherland here in South Africa. We learned a lot from that. One of the things that we also learned is that this site is not very good. So we're very happy that we had already picked Chile for BlackGEM. And there we are at La Silla, one of the ESO sites, the older ESO site, where this building here, the GPO telescope, was demolished, and that's where we built our telescopes. And so that was ongoing in 2019, and then in 23 we finished that. So to give you an idea, this is the installation of one of the telescopes on the tower here in the back. This is the dome. We got that as a sort of an IKEA package from the manufacturer. We have never built such a dome, but we thought, well, we can do this. So we were building it here on the platform next to the dome. That took a while because we also had to test it. Once it's up there, it's very hard to change anything anymore. These are all the crates which contain all the components of the telescope itself. So many people working on the dome. This is the counterweight of our telescope. So this was working quite well. And then there was one guy who didn't want to go to lunch. Now it's lunchtime. Watch the sun here. It gives you a sense of the time of the day. So there goes the dome. Now somebody is screwing the 25 bolts on the inside to fix it to the tower. And then it will be time to put all the other components in. This is the pier under the mount. Then parts of the mount. There goes the mount itself. You have some ladders, whatever. Counterweight here in front. And in the end, the telescope will come from the back. Keep watching the sun. We finished right in time that day. And luckily, because as you can see here at the end of the movie, the weather turned bad quite quickly after sunset. So that was the installation of one telescope, or at least putting all the parts in place. And then comes several months of installing cabling and electronics and making sure that it all works. Then, of course, we had COVID in between there. And when we came back after the COVID delays, our primary mirror looked like this. That's not how a mirror should look. So about half the surface turned gray. So this is a silver coating, which is protected with a silicon oxide to keep the oxygen out. And that didn't work very well. So the silver started oxidizing, and that meant that we already had to recoat our mirrors before we even started. While we had expected for this to last 10 years, that's at least what the manufacturer promised us. So we had to do a whole effort to take the mirrors back out, get it cleaned, get it recoated. Of course, I'm telling you the full honest story. There was another mistake. In some orientations, the telescope could touch the dome. Now, that's not what you want, certainly not for a robotic telescope, where the dome closes itself in case of bad weather, for example, and it doesn't care where the telescope is. So they fixed that by raising the outer part of the tower. So these towers, they're 7 meters high to be above the turbulence of the ground, what they call ground layer seeing. During the day, this heats up, and then during the night, you will get turbulence above the ground surface. So we're 7 meters up. Because of that reason, you'll see the same thing when you go to Mercator, for example. It's also on a high pier to be above the ground layer seeing. Now, our tower here has two towers. There is an inner tower, which goes in the middle and holds the telescope, and then there's this Eiffel Tower structure type thing, which holds the dome. So by raising that outer tower, we could solve this problem. And then the current status is that 2 of the telescopes are operating robotically. I just came back from Chile. I was there last week to make one of them operational. And we currently have one telescope, the middle one, which is not yet operational because we have contamination on the CCD. So that is currently being cleaned. And then we'll go back to La Silla to also make that one operational again when the detector is back. Typical images, well, of course, this is a beautiful field, a busy field, but the typical image then looks like this. So this is not a mosaic or anything, this is a single exposure. And of course, it's 110 megapixels, so you can zoom in quite deeply. And there's hundreds of thousands of sources in a busy field like this. The data quality we're getting, these are the 0 points right now in our most sensitive band for the 3 telescopes. That gives us a limiting magnitude, singleton noise 5 of 21.6 in that wide band in our typical 1 minute exposure. And the image quality we're getting now is 1.3 arc seconds. That still needs to be improved. 1 arc second is the design spec. And we know what we can do to get there. The bottom plot here shows the RMS on the magnitudes that we measure for the targets as a function of the mean magnitude. And so this 1 millimag is on the bottom here. This is 10 millimag. And saturation starts to occur here between 12 and 13. And this is also following what we expected in the singleton noise calculator. Now, there's a lot of data being generated by a telescope like this, of course. We take, with the 3 telescopes, around 2,000 images per night. That's 150 gigabytes. And there is very much a first mile problem because there is no fiber to La Silla. So that we have a microwave link to get it off the mountain to a different place where there is a fiber. And then all the data goes into Google Cloud and goes over Google networks to Europe. The processing itself relies on a lot of standard processes, of course, and we're very much tied to Gaia. So all the astrometric calibration is done based on Gaia, including proper motions that are measured. And the photometric calibration is also done based on Gaia, based on the low resolution spectra that Gaia has made available. And then the pipeline has two parts. There's a variability pipeline. We do forced photometry on all the sources that we expect to see in the image based on the Gaia catalog. So for every source that is in the Gaia catalog and that should be in the footprint of our image, we do a measurement. Whether it's there or not above the noise, doesn't matter. We will measure an upper limit then. And that gives us around 100 million entries, source detections per night. Now that is, of course, that's a very large database that comes out of there. There's also a very time-critical part to this, of course, and that is to find these transient sources, the light from the double neutron stars that explode and other transients. For that, we use difference imaging, so we subtract an older image, a template image, from every new image that comes in, and then we look at the differences between these two. So there we do a blind search using source extractor to find the transients, and that gives us several thousand candidates per night. And then we have a classification pipeline that does a first attempt in separating the real objects from artifacts that are also in that data stream. So an example of a real transient, for example, is this. So you have the new image cut out on the left. You have the old reference image on the same location in the sky in the middle. There's a difference image then on the right. So this is clearly a real object. It's a real transient. It's a supernova on a galaxy. And if you subtract it to the galaxy is gone, and you're left with light from the supernova. This is very much what a double neutron star merger would also look like, but then a bit fainter. This is another real transient here. Here you see that it helps a lot to do this image differencing, because now the contrast it makes it much easier to see that in the middle here, indeed, there is a new source, a transient. It doesn't tell you what it is, of course. It can be something explosive. It could also be an eclipsing binary that is in eclipse here and out of eclipse there. It can be anything. That's then another step you have to make to find out what it is. Now, as I said, it's not all real what we see coming out of our pipelines. There's also a lot of things that are not real. That can be artifacts from the telescope. It can be in the image processing that something goes wrong. There are also things on the sky that we don't want to include. For example, the top one here. Does anybody have any idea what that might be? So it's a plane. Satellites look similar, but they have a relatively constant brightness. Planes have these lights on their wings. So if you look at the full image, you will see a trail and then dots, equidistant dots, whenever these lights blink. So this was picked up as a source because it looks like a source, but if you detect that there is this line in the back, then you see that this is a plane. The bottom one? Yes, of course, a UFO. Not a UFO, this is an instrument artifact. So this is a bright star in a different channel of the detector that saturates some electronics and is corrected for in a slightly different way in the reference image and in the new image. And so there's an imprint of that saturation left in the difference image. So unfortunately, not a UFO. So we did a lot of manual vetting of such candidates to build up a training set for machine learning. And we started with 5,000 examples, and we had 10 people from within our consortium, so experts, looking at those, classifying them as real or not real. And in the end, you see that also these experts don't always agree. So we had, in 94% of the cases, 8 people out of 10 or more agreed. And that's what we used then as our training set. That's a start. That's not the final solution. This needs to be improved. So we also built a citizen science app, which is called Black Hole Finder, and you can find that in your favorite Google or Apple app stores. And And there we feed these transient candidates that we detect in real time to the users. So within half an hour after the image was taken, it's processed and it's uploaded in the app. And then you see the same things as what I showed you before, a reference image, a new image, and a difference image. And people are asked to help us judge whether this is real, bogus, or unknown if they don't know. And so this has two goals. One goal is to build up a better training set, and the other goal is to get live input, so that in the morning when the people in our science consortium wake up, they're already part of the transients that they don't have to look at anymore, because people have said that this is not real. And this is quite popular, so we've been running it now since November, and the top users have tens of thousands of classifications made already. Then we're building up databases for the transients, so we're matching detections by coordinate, build up light curves for detections in that way. This is one of the examples. So here you will find variable stars, you will find eclipsing binaries, you will find explosive transients as well. And then for the photometry, for the variability photometry, we built a database in BigQuery, which is one of the Google Cloud database solutions, which scales up very much when you ask a difficult query, and scales down to 0 resources when nobody is using it. So here we have uploaded the whole Gaia DR3 source list, because all our photometry is tied to that. So people can use all the columns in the Gaia DR3 to make selections, and then they can retrieve the measurements, magnitudes, positions, etc. of these detections in all our images. And of course, there is all the metadata from the images available. And we also have a number of statistics about the variability of these sources that is computed, so that you can use those statistics as well to find the interesting ones. And this is where I'll hand over to Jan to discuss the surveys and the science.
All right, good. Work? Yes, great. Yes, so as Steven already mentioned, BlackGEM was built to find kilonova counterparts to gravitational wave detections made by LIGO and Virgo, but BlackGEM can do many other things. Basically, you can see any kinds of variability in the night sky. And Steven mentioned already, we have quite a large consortium now in the Netherlands, Belgium, Germany, UK, US, and a few other places which I'm forgetting now. Denmark is one of them as well. And most of these people are actually interested in that other kinds of science. And therefore, I mean, there's not always gravitational wave triggers, although that is the highest priority. There's also other things that BlackGEM will be doing when there's no trigger to follow up. So in addition to the trigger mode, when LIGO Virgo puts out an alert and we start searching, in the meantime, when we're waiting for that, we actually have a program to look at the local galaxy or the nearby, the local universe, nearby galaxies within 150 parsecs. And we try to find nearby exploding stars very early. We also have a fast synoptic survey where we stare at a field for a long time, typically at low galactic latitudes to study short timescale variability of stars. And finally, we also do a southern sky survey. Right. So as Steven mentioned already, what happens if LIGO, Virgo, Kagra, or any of the future gravitational wave detectors find a gravitational wave source? BlackGEM is automatically triggered. It will, within 5 to 10 minutes, start basically searching the error box, basically where these gravitational wave detectors indicate the kilonova should be. And we basically will start to search that part of the sky in 3 filters, or maybe 1 filter if it's a very huge area. And then we will do that for a week, or until we have a definitive identification of the counterpart. So this really is the science driver of BlackGEM, and I think LIGO Virgo have been switched on yesterday, or at least for an engineering run. So it's a very exciting time for us, because this is now the time to get this done. Right. No. Uh-oh. Yeah, there we go. So as I already mentioned, we are also very much interested in other kinds of explosions in the nearby universe. We've taken a catalog of all the nearby galaxies, and we figured out what basically ranked all the BlackGEM fields by which contain the most galaxy mass in the nearby universe, and basically prioritize the fields which contain the most galaxy mass, and therefore should be the locations where we find the most nearby transients, such as supernova. For example, a group in Israel is very much interested in observing supernova 1A is very early to get a very early spectrum to study the flash features in those spectra. In addition to the nearby galaxies within 150 parsecs, we're also looking at a few special fields like the LMC, SMC, and I think we also have a few fields in actually the galactic bulge that we're monitoring for actually some galactic signs. In addition to that, so these fields we will look at twice or 3 times per night in U, Q, and I filter. We also have the 2B, which is here. So once every week, we also want to just keep track of what's happening in a larger footprint, just to make sure we know what's going on when we get a trigger, that we're not confused by older transients. So that's why BlackGEM is also observing a much larger footprint, which goes up to 40% of the nearby galaxy mass, which we do once a week in just Q band. But so that's also very useful to study slower transients. Right. Keep forgetting. Yes. So as I already mentioned, we're also very much interested in galactic science and short period variability, for example, for astroseismology and compact binaries. So what we do with those fields, specifically the low galactic latitude fields where there's loads of stars, we look at those fields in the U, Q, I, and Q band again. And then continue that for 3 hours or longer. It depends a bit on the visibility of the field. And we do that for 2 nights in a row. So we really probe the very short time scale periodic and aperiodic signals of stars. The goal is to do about 1,500 square degrees per year with this survey. As I mentioned already, we focus on low galactic latitude fields, but we're also very much interested in unique stellar environments like open clusters, for example, or star formation regions. I think we need to replace the battery soon. Right. Finally, there's the 4th program, which is to build up a static all-sky image of the southern hemisphere in all filters. So that's U, Q, and I primarily, but we also aim to do GR and Z as well. Initially, we wanted to do everything with BlackGEM, just BlackGEM. However, there's a few other surveys which have already done some parts of the sky in a few filters. So we decided to be efficient here and not repeat work that's been already been done. So we will do the whole sky in U, Q, and I, but for the GR and Z filter, we will visit the areas that haven't been visited yet by other telescopes. And this will, by the way, will be a public product, which will be hosted by ESO, which is the fee to be on La Silla. Right, so I just want to end the talk here with a few examples of what we've found already with BlackGEM, just to give you a sense of what the data looks like. And as I mentioned already, with BlackGEM you can basically do time domain astronomy, so you find stuff in the solar system, in our own galaxy, or you find extragalactic objects. Basically stuff that moves, stuff that varies, or stuff that explodes, roughly divided by these topics. Right, so to start out with solar system science is actually not the biggest part of BlackGEM. I don't think we actually have anyone working on it directly at the moment. However, we are finding loads of asteroids, comets, and satellites, and we're slowly, well, we mostly want to get rid of them, but there are some fun things that you can do with it. I'll start with the image at the bottom. We were looking at our transient discovery stream yesterday, and usually asteroids are automatically removed from our data stream. However, this one was not, and the reason was because this one's actually new. So this is probably the first asteroid discovery we made with BlackGEM. And we don't have a pipeline yet, but this should be something we can do more automatically. Just to give you some numbers, we detected almost 50,000 solar system objects already in the BlackGEM images, and well, BlackGEM also helps protect the Earth because it's identified or helped improve the orbit of 33 potentially hazardous asteroids. So there is some contribution to the solar system science as well by BlackGEM. So just to show you an extragalactic transient, I'm not going to read out the whole name, but this one was actually the first one BlackGEM discovered, and the case where BlackGEM was the first to report the existence of this explosion. So you see that we detected it at about 20th magnitude over here. It slowly rose and then faded again. Unfortunately, no one actually identified it. I guess it's some kind of supernova by the looks of it. But there are a few other examples that look much nicer. So on the left you see a very nice light curve in the U, Q, and I band, so purple, yellow, and red. And this is a very nice example of a supernova 1A, where you see this plateau, this second bump in the I band, very characteristic for 1A supernovae. On the right you see an example of a transient in the LMC, the Large Magellanic Cloud. This turned out to be a nova explosion, and one of the very nice things you see here is that these purple dots, the U-band light curve, shows that this object was very early times very, very blue. So that's one of the unique capabilities of BlackGEM, is to do this U-band observations of transients, and it's one of the exciting things, or people are excited about from the transient community, because no other transient survey is doing any U-band observing. Right. So I couldn't help myself but to insert my own favorite science here. So these are, this is an example of compact binaries that I'm very interested in. So it's a white dwarf accreting from some kind of degenerate object. And these things have orbital periods of about 5 to 60 minutes. So they are also gravitational wave sources, just not detectable by LIGO Virgo, but they will be detectable by LISA. So as I mentioned, this thing, these two stars are orbiting each other, in this case, every 39 minutes, and this one happened to be eclipsing, so every 39 minutes, this source almost completely disappears. So it goes from 19th magnitude to almost 21st, and that happens every 39 minutes. I guess we missed one eclipse there. I guess it was in between exposures, but this is one of the things a few people in the collaboration want to use BlackGEM for, to find these very short period white dwarf binaries. And just to show you another example, you also have the non-accreting version, where you've got a white dwarf and another white dwarf. And one of my colleagues is already searching through all the BlackGEM data we have, and he got very excited, because here you see one night of fast synoptic data and another night, and he did a period analysis, and there's a He found that this object had a period of 47 minutes, found a very strong peak, and folded the light curve, saw it was an eclipsing double white dwarf. There's one eclipse here, which is very clear, and the other one actually much shallower, which is also still visible there. And this object is on the well, in the white dwarf region of the HR diagram. So he was already writing his follow-up proposal, and then unfortunately I had to disappoint him because this was one of the objects which was already known, and we observed to test the BlackGEM capabilities. But it does show that BlackGEM is able to find these things, so that's also very good news. So my final slide, or almost final slide. So what is the near future for BlackGEM? So as I mentioned already, LIGO, Virgo have started their 4B campaign yesterday. So in their schedule, we're now like halfway there. We also have a team meeting next week in Nijmegen. If you are interested, you're welcome to join. It might be a bit short notice to still come in person, but we have a Zoom link. You are at KU Leuven, so you are all invited to join the BlackGEM science team. With regard to telescopes, so 2 of them are operational. One of them still needs a CCD bag, which is ready to be shipped, and probably Steven will go back to La Silla to recommission BlackGEM 3 soon. And observing-wise, what we're doing now is we already took test data for all the different programs. What we want to do now is just get reference image for the whole sky, so we have something to compare the new images with, and that's what we're using the telescopes for at the moment. The yellow fields are where we already have data, but the initial data wasn't quite the quality we wanted. So now we're redoing this, and those are the blue fields. So we started at the southern pole, and now are about minus 25 declination. So already quite some area has been covered, but still need a few weeks to fill in the whole visible sky. I think, yeah. This was the end of the talk. Thank you for your attention. If you're excited to use BlackGEM, come talk to us. We're very eager to have you join the team. Thanks.
Thank you, Steven and Jan, for a very interesting talk. Does anyone have any questions?
Thank you both, great talk, and of course a great project, as you know. Well, 2 questions. The first one, most of the surveys are done with 3 filters. How did you pick them and why?
It's a science question.
Yeah, so the Q band is really the broadest band, so that gives the most signal per second, basically. So that's why we've chosen that one to really go as deep as possible for anything that's visible. The U and the I band have been chosen to just get more color information.
So, and then come the remark or the suggestion for the SMC and LMC. It turns out that, I mean, I am more and more convinced that this is the laboratory in which we will understand better stellar physics. So I would encourage you to hammer the SMC and LMC maybe with more colors. Also because of synergies with larger, I mean not larger, but because BlackGEM is very large, but other surveys in which KU Leuven is involved. It's with the VLT, it is with the Foremost, and now it is with UVEX that will come in 5 years from now. That will also look for gravitational wave transients in the UV, and having a very good understanding of the stellar content of both clouds and the metallicity dependent, I think is important, and BlackGEM is ideally suited to make a big impact there.
Yes, I was actually talking to Tomek about this a few weeks ago. You mentioned you had some spectroscopic campaign going on.
That's one part, yes.
Yes. So the LMC and SMC, we have them in the local universe schedule, so they will be observed twice or 3 times per night, depending on visibility, in U, Q, and I. So we've got 3 colors and then 3 visits per night. We have actually also done 1 field for a few hours continuously. We still want to look at the data first before we continue, but yes, we're definitely observing those two fields regularly.
Thanks very much, both. You mentioned the science case of the very short 1 hour white dwarf binaries. I'm personally more interested in the half a day, 1 day variability contact binaries. What do you expect is the yield of this project, let's say, per year? How many contact binaries do you expect to find?
Contact binaries.
Or let's say very near contact binaries.
Sorry for that.
Like very, very short period binaries, 1 day orbits.
So the double white dwarfs and then like less than 60-minute systems, those are very rare. So
Yeah.
we probably need to observe quite a bit of the sky to find one.
Mm-hmm.
I think for the contact binaries, they should be easily detectable in the
Yes.
actually not the fast synoptic survey fields, but also the local
Yeah.
the local transient survey fields. They are focused, or those fields have been chosen because there's a galaxy in there, but of course there's loads of stars in the foreground as well. So in those fields, there should be plenty of those.
Do you have an estimate? Like I know the Rubin survey will find 1 million roundabout. Okay, no worries. But let's keep an eye out for them.
Hey, great talk. I was just wondering, compared to, say, let's just use O4, so LIGO's O4 sky volume for neutron star merger, how does that compare for BlackGEMs? And do you see that diminishing a lot, that fraction, as you go into O5?
Well, I think in O4 we can reach the distance that LIGO Virgo does, but probably not much more. So what they gain in O5, we probably don't. I think that's the. Yeah.
Okay, thanks.
Hi. I was wondering, since you're taking so many images and visiting regions again, I guess, are you also measuring the positions of all the sources or not? Like, could you do something like Gaia astrometry from the ground with BlackGEM?
So we initially had a pipeline which did source finding on the BlackGEM images themselves and then tried to combine everything in the database. That didn't quite work as we hoped, so then we decided, well, Gaia already has measured the position much more accurately than BlackGEM can ever do, so why we don't use that and just take that information and do better photometry. So in practice, yes. In theory, yes. In practice, not really.
So, for example, like hyperpromotion sources, can you like follow them in a sense? Can you identify that's the same source in a different image?
Do you know anything about the positional accuracy of BlackGEM?
If we would measure it, it would probably be 0.2 arc seconds or so, the positional accuracy. But we only measure positions for transients. So in the transient data stream, we do measure positions, not for all the stars that are in the field. It can be done. Yeah, no, it's not competitive with Gaia there.
Okay,
Except for
thanks.
transients which weren't seen.
As with the gravitational wave detectors, are there already plans on the table for upgrades or dreams maybe?
Well, you know Paul, right? He dreams big. His wallet is not so big, so it all depends on the money. Yeah, he has a Photoshop picture of the BlackGEM sites, but then with 15. So that gives you an idea.
Hey, I have a bit of a follow-up on more or less how do we compare to the LIGO volume, because my understanding is for 1708-17, they were relying on this less than 40 megaparsec galaxy catalog. and they were actually really lucky that the galaxy was outside that range, but actually inside the catalog. So isn't it a situation where you might be able to reach in principle so far, but galaxy catalogs are incomplete through all the distance?
Yeah, the galaxy catalogs are definitely incomplete. So once we have a LIGO Virgo gravitational wave trigger, we will definitely just search the entire airbox. We won't focus on galaxies. Just the local transient universe. Well, it could give us a head start, and there's let's say we already observed 13% of the mass of the local universe. So if we are basically 1 in 9%, 1 in 9 events, we already pre-observed those fields. So just to give us a little bit of a head start if we're lucky.
Okay, I had another quick question, like in terms of just mapping more of the sky, are there plans of similar infrastructure in the northern hemisphere or just in a different meridian of Earth?
So the field of ground-based optical time domain science is getting quite busy. I worked in between Nijmegen and Amsterdam. I worked at Caltech with the Zwicky Transit Facility. I can definitely say don't try to compete with them in the north.
Okay, thanks.
And well, in addition to that, there's also the GOTO and Atlas surveys, which are both in the north and south. So BlackGEM will definitely go deeper than those, but they have a larger field of view. So.
Hi. So I have a question about the observing strategy. So how would the 3 telescopes work together, like the different filters and different fields? How is it going to, what is the strategy?
I guess I'll answer this. The telescopes, once they're all operational, 2 will do the local transient survey, 1 of them will do the fast synoptic survey for more galactic science. If there's a gravitational wave trigger, all of them will follow up that gravitational wave trigger.
Right. So yeah, I'm hopeful that O4B will maybe bring us a multi-messenger BNS event, but we'll see. But I had a question regarding multi-messenger follow-up. Are there any plans, or are you considering also following up on neutrino events that get detected by, for example, IceCube?
We currently don't have anyone in the science team interested in that. Okay. I stand corrected. We do have someone interested in following up those events. No, we're definitely open to additional science cases, and BlackGEM is made to follow up events on short time scale, so neutrino detection. So definitely.
Yeah. I would just have to check because IceCube detects through the Earth, so you might not be looking for the wrong sky, but then maybe a northern hemisphere neutrino detector might be better suited. But I'm sure Rose will correct me.
Yeah, IceCube surveys the northern sky, but there are ongoing plans to build. There are ongoing buildings work done in the northern hemisphere to survey the southern sky with things like RNOG, KM3net, universities like the VUB are taking a leading role in. Yeah.
Okay, thank you. Very nice talk. I saw galactic variability and extra galactic transients, but with a limiting magnitude of 21.6, you could also do the more brighter stars of extra galactic or to do for variability studies. Is it on purpose that you focus on the galactic ones only?
It was maybe too much of a simplification. We're definitely, I'm definitely interested in all things you can find in time domain surveys. We just have a small team and no one's looking at that at the moment. So if you're volunteering.
Connie.
Yeah, as you know, people like me are not interested in the faint universe, but in the bright universe. So you haven't set what the limiting magnitude is before you start saturating at the bright end. Have you done tests with that or not yet?
Yeah, so I think maybe you showed the slide. Steven showed the slide where we, yeah, it's about 13, yeah.
And what happens if you go below? Yes, I know, but we can work with saturated images these days, you know. We know how to do halo photometry, etc., from our space missions. So is anybody looking at that or not at all? No. Can you use, yeah, okay. I'm not saying it's easy.
Sounds like a fun challenge for a student here.
my master student will do that.
Are there...
But finally somebody's asking to not improve the image quality yet.
Well, I think we're not going to defocus BlackGEM, no.
As we're almost at the hour, are there any last questions? If not, I think we can thank Steven and Jan for their excellent talk again. Thank you very much. Thank you for attending and see you next week.
We will be here for 2 days, so...
Yeah, they're around for a couple of days, so if you want to have discussions with Steven and Jan today or tomorrow, they'll also be in various group meetings.